In chapter 16, we talk about chemical equilibrium. This will just be the overview video for the first part of chapter 16. Throughout the chapter slides, you see this F symbol, which I don't know why that's there. I think that's just the slides formatting error. And that should be a dynamic equilibrium equation symbol, which is usually a double arrow like this. So wherever you see this F, just picture it's a double arrow, dynamic equilibrium arrow. So what is dynamic equilibrium? And this basically means, and we'll skip the lung example for now, we'll talk about how when a reaction occurs, you know that everything starts out as reactants in the mixture. Then over time, the reactant concentration decreases, the product concentration increases. Then what happens is that we can consider that to be the forward reaction. So there's a forward reaction and a backwards reaction when we have this dynamic equilibrium going forward and backwards at the same time. So when the reactants decrease, the forward reaction increases because those reactants are being turned over into products. But when the products increase, the forward reaction decreases after a while, and the backwards reaction will start to increase. So you can picture this, that's what we call a dynamic equilibrium, because both things are happening at once. The reactants are decreasing, the products are increasing. The forward reaction starts out very high, but then decreases, and the product reaction, or the backwards reaction, starts out very low, but then increases when there's more product. Eventually, we reach an equilibrium where the rate of the forward reaction is the same as the rate of the reverse reaction, which then that's what we call dynamic equilibrium. Now, the concentrations of reactants and products do not have to be the same, and usually they're very different. But the rates of forward and reverse reactions are the same in order to not lead to a net increase or decrease in any of reactants or products, because then it wouldn't be what we call equilibrium. So we can call these reactions reversible as well. So here's just to reiterate, dynamic equilibrium is the condition wherein the rates of the forward and reverse reaction are equal. It's not the concentrations, it's the rates. So here's an example of that occurring. If originally you have these kind of grayed out reactant particles. At time zero, the mixture is all reactant particles. Then as you increase time, what happens is the forward reaction begins to increase and products are made. So now it becomes 6, 6, and 4. Then what happens is it reacts more and the forward reaction still happens. And then eventually you'll reach a time where the forward reaction stops occurring. Now this is where equilibrium occurs, and the rate of the backwards reaction, even though you don't see it here, is still a thing, but it is equal to the rate of the forward reaction. So when those rates are equal, again, that's when you have dynamic equilibrium. And you can kind of see that in these concentration versus time diagrams of the reactants on the top left and the products on the bottom left, where HI as the product is originally no concentration, but then it increases and it reaches an equilibrium concentration, which, as you can see, is different than each of the reactant equilibrium equation or concentrations. So again, it's the rate. So what we can say, we'll skip these examples for now, and what we can say is we can develop an equilibrium constant, which we'll talk more about in class. So this equilibrium constant can be determined from a reaction, and can also be used to tell whether the products are more favored in the equilibrium or the reactants are more favored in the equilibrium. And this K, which is our capital K, lowercase k is our rate constant. Capital K is our equilibrium constant. So again, if this is complicated, go back to chapter 15 and look up reaction rate is a lowercase k, the rate constant. This is an equilibrium constant, and it is unitless. We know that K, lowercase k, has units for the reaction rate constant, but the equilibrium rate constant does not have units. So what we can say about the equilibrium constant is that it is a quotient of the products over the reactants, where the exponents of the products and the reactants are the coefficients. So for example, if we have this reaction 2A plus B equals 3C, we can say capital K equals the concentration of C cubed divided by the concentration of A squared times the concentration of B. And that is option letter C. And it's very simple. It's the same for every type of reaction. So if you see the reaction, the reversible dynamic equilibrium reaction, you can determine the the equilibrium constant very easily. Here's another example where you have the N2O5. So it would be in the denominator. So it would be products over reactants. So NO2 to the fourth times O2 to the 1 over the reactants, which is N2O5 squared. So that would be your equilibrium constant. Now, what can we determine from this equilibrium constant? We can say that when K is much greater than 1, that the equilibrium favors the concentration of the products more, meaning there's going to be more products than reactants when the equation reaches equilibrium. So we can see that if this number is larger than 1, that means the ratio between products and reactants is going to be very high, more towards and more in favor of the products. So that's why the equilibrium will be in the direction of the products, and it will favor the forward reaction. That's another way to determine it. So it favors the products and it favors the forward reaction. Then if you have a K value of less than 1, this means the reaction reaches equilibrium. There are many more reactant molecules present because the ratio between the products over reactants will be less than 1, which means the reactants have to be higher. And this favors the reverse reaction. So that's a key thing to keep in mind. Now here's an example of a large and a small, and here's an example of a question. Now, what can we say about this? Is that the equilibrium constant for a reaction is 10. So if this reaction is 10, a reaction mixture initially containing 1.1 molar of A and 0 of B, which statement is true at equilibrium? Since it's 10, it tells us that our products are at a much higher concentration than the reactants. So we can say that the reaction mixture contains 1 and 0.1. That's not true at equilibrium. We want a lot more of the products. So it contains 0.1 and 1. That's most likely to be true. And that's the answer, because we have a high favorability of the forward reaction because the equilibrium constant is much larger than 1. So our products will be in higher concentration than our reactants. So we can manipulate this equilibrium constant a bit, and we can say for a reaction in the forward direction, it's the products over the reactants. But for the equilibrium constant in the backwards direction, meaning if you just flip the equation, we can write it the opposite. We flip the numerator and denominator. And that makes sense because if we're writing the reaction forwards and backwards, this is on the left you have the forward one, on the right you have the backward one. The forward one, it's just products over reactants, but the backward one is flipped. So then it's again, once you write the flipped equation, products over reactants. But we can say, and we can come up with the relationship that the equilibrium constant for the forwards reaction is 1 over the equilibrium constant for the backwards reaction, or like this equation suggests, vice versa, because those are interchangeable. Just to understand that it can go back and forth. And this kind of gets into the fundamental ideas of Hess's law that we talked about in chapter 7 from Chem 1, is that when we manipulate an equation back and forth, we can manipulate, not the enthalpy in this case, but we can manipulate the equilibrium constant. And we can do that in more ways. So what we can do is if we multiply an entire equation by an integer, let's say 2 in this case, if we multiply it by 2, that 2 goes to the exponent of the entire equilibrium constant for the before case. So what we can do is multiplying this left equation by 2, we could put everything in parentheses squared, which would then lead to our new equilibrium constant, which would be concentration of C to the 2 times its original coefficient over you can see that everything is individually squared. So if we multiply it, we put another 2 in the exponent, multiply the exponent by 2. And then we can add them. When we add them together, what we do is simply multiply each of the rate constants, or no, multiply each of the equilibrium constants together. So if we're adding the equations, A goes to B and B creates C, we can come up with the equilibrium constant for equation 1, which is B to the B over A to the A, equilibrium constant for reaction 2, C to the C over B to the B. Multiply these together, B's to the B's cancel out, and you end up with C to the C over A to the A, like that. So the K nu, meaning the overall equilibrium constant, equals the first constant times the second one. So here's a good example that we can do right now. If you have this reaction with an equilibrium constant of 0.01 in this reaction, what is the equilibrium constant for this reaction? So A to 2B. This is B to 1/2 of A. So to get from here to here, we take the rate constant, or we take the equilibrium constant, and we divide it by 2 and flip it. So that's exactly what we're going to do. Instead of dividing it by 2, we take it to the 1/2. So 0.010 to the 1/2, and then we flip it. So that means it's to the 1 over that. You get 1 over 0.1, which is equal to 10. So we can relate this equilibrium constant to gases. So what we can say is that because we know that a concentration of a gas, if it's an ideal gas, is proportional to its partial pressure, we can say that instead of the concentrations in our equilibrium constant, we can make it partial pressures. This gives us two different numbers, two different constants. Our equilibrium constant called Kc, which means the equilibrium constant with respect to concentration, which is the one we just went over, the main one. Or we can have Kp, which is our equilibrium constant with respect to partial pressures of gases. You can have both of those, and they may not be the same value, because in this, even though it's unitless, in this equation you're dealing with ATMs, and in this equation you're dealing with concentrations, and the partial pressures may be a little different. So what we can, and depending on the gas reaction, so what we can do is we can develop an association between Kp and Kc. Again, this formula is going to be given, and what we can say is that Kp equals Kc to the RT, and this R is in 0.08206 because we're not dealing with joules here, times temperature in Kelvin to the delta N. Now, delta N is the difference between the number of moles in reactants and products. So, for example, if you have 2A plus B in an equilibrium with 3C plus 2D, and these are all gases, the delta N will be the difference, the number of moles on the right side, which will be 5, minus the number of moles on the left side, which will be 3, and that equals 2. So delta N would be equal to 2. Now, when delta N equals 0, what happens? This RT term becomes 1, and we have Kp equals Kc. So this factor, this RT to the delta N, is just to correct for the difference in moles in certain pressure-related equations. Because if you have pressure involved and you have more moles than you started out with, that increases the partial pressures, but it may not increase the concentrations of each of the product and reactant with respect to one another. So, so just keep in mind this equation exists, and we use the change in moles only for gas equations to relate the equilibrium constant with respect to concentration and the one that's with respect to pressure, to partial pressures. So we can also talk about a heterogeneous equilibrium. So everything we talked about so far, we just simply take the reaction and we do the products over the reactants with the coefficients in mind as the exponents. But if you have pure substances involved in a reaction, such as pure liquid water or solid carbon, things like that, they are not included in the equilibrium because we don't talk about pure substances as having a concentration. So concentration only talks about gas. We only talk about gases and aqueous solutions. We never talk about liquids or solids when it comes to concentration. So that may not be a super apparent to everybody, but just keep that in mind. And the reason why is because a pure substance is not going to mix with anything else. If you have a pure substance that's a solvent in a solute, then it's no longer a pure substance. Then it's part of a solution. And solutions, as we know, have concentrations. So what we can say for this reaction, the equilibrium constant will just be H plus times HCO3 minus over CO2. We would not have the H2O because it's a pure substance. So keep that in mind as well. And here's another example of that when you have solid carbon, is that when the reaction continues to happen, the products are going to be the same. They're going to be in the same concentrations, but you have this non-mixing pure solid in there that will contribute to the reaction. But again, its concentration cannot be a factor in the equilibrium constant. So what we can say is that we can also determine the equilibrium constant, either Kc or Kp, from experimental data. And you can see that no matter at what point in the reaction, our Kc is going to be equal. If we have different concentrations. So if we have different if we have different reactions going on, and if you have different equilibriums. So even if you have different equilibrium concentrations, the ratios between those concentrations will be the same in order to figure out the same Kc. And we'll learn about an ice table. So a main part of this, the second half of this chapter, is to set up an ice table to figure out missing concentrations. But we'll do that in the second part of this video. But what we can do first is we can talk about another definition called the reaction quotient. Now, what the reaction quotient is, it's very similar, but it is different than the equilibrium constant. So the equilibrium constant, Kc we'll call it, it's used so only at equilibrium concentrations. So what this means is that this Kc, we only figured out this value. The only way to figure this out is taking the equilibrium concentrations and doing the math. The reaction quotient can be used for non-equilibrium concentration ratios. This means it's calculated the same exact way, but it can be at any point in the reaction. So we can calculate it identical. So you have QC and QP instead of KC and KP. So basically, they're the same thing. You calculate them in the same way, products over reactants with the coefficients being the exponents, but Q is at any point in the reaction. K is only at equilibrium, and is an equilibrium constant is specific for the reaction, and it does not change unless you do something to the reactants or products. So what we can say is that when Q is larger than K, think about it as a ratio of products over reactants. If Q is larger than K, this means that there's too many products, and in order to get to its equilibrium K, it needs to get smaller. For it to get smaller, this means that the reaction will proceed fastest in the reverse direction. So Q, being larger than K, has more products. Thus, to get to K and to reach equilibrium, it needs to have less products. So the products will decrease and the reactants will increase. In order for that to happen, you need the reverse reaction to increase. And on the other hand, if you have Q is less than K, that means Q is more heavily towards the reactants. And this is true for the beginning of most reactions, is that when you have mostly reactants, the reaction is going to travel in some extent in the direction of the products. Even if it's not a lot, it will initially go towards the products. Otherwise, you won't have a reaction at all. So if Q is less than K, this means that K is larger, and it's a larger ratio of the products to the reactants, meaning the reaction will proceed in the forward direction faster. And if they're equal, it means that it's at equilibrium. So here's a summary of those ideas. Now we can do another example, and we're almost done with this review. For this reaction, N2O4 yields 2NO2. a reaction mixture at certain temperature initially contains both these, their reactant and product, at the same pressures. If Kp is 0.15, which statement is true for the reaction mixture before any reaction occurs about Q? Now, Kp is 0.15. This means the reactants or the products are favored. It means the reactants are favored because it's less than 1. So if the reactants are favored and we have 1 mole or 1 atm of the reactant and 1 atm of the product, which direction is the equilibrium going to go? Or which direction is the reaction going to go? It's going to go towards the reactants. The reason why is because we want to reach our equilibrium, and we know our equilibrium concentration ratio, meaning Kp, is more towards the reactants based on our Kp. So we can tell, I mean, if we have the products and reactants at the same concentration, we want more reactants than products, so the reaction will go in the opposite direction, the reverse direction. So it means that Q will be larger than K, meaning in this case Q is 1/1. The reaction will proceed to the left. So that would be C as our answer. And keep in mind, they gave you Kp, but you can calculate Kc from this. So the way we can do that is Kp, which is 0.15, equals our Kc times RT times your delta N. And delta N in this case is not 0, because in this reaction that contains gases, you have 2 moles of product and then 1 mole of reactant. So our delta moles will be 1. So the only thing you're missing is the temperature in this case, but you can calculate Kc from it if you have the temperature and the equation. That's all you need. Well, and Kp. So that's a good little thing. So then on the next video, we'll be talking about ice tables, which is more mathematical and is kind of like solving a quadratic in some cases. And we can solve for X, and we can figure out what is the missing concentrations at equilibrium of a certain reaction, just knowing the reaction quotient or just knowing the reactant or the equilibrium constant, and knowing some other, and knowing maybe only one concentration. So there's basically, you're going to have some unknowns and you're going to be able to figure it out using the ice table.